Okay, so let's go over a couple of examples that we did in the presentation to illustrate this whole concept of linearization of nonlinear systems. So I'm going to run the examples that we did, and I'm going to do the zoom in thing that I actually talked about in the first part of the lecture, but this time with nonlinear systems. So this is the first example we entered. We discussed in the lecture 1 minus x squared plus 1 for x prime of t, and y plus x squared minus 1 for dy dt. So remember the equilibrium points in this case was minus 1, 0 over here, where I hover the mouse, and 0, 1, 1, 0 over here on the right side. So let's click on a couple of solutions until we fill in actually this phase plane, and then I want you to focus what happens around each equilibrium point. So I'm going to click on, I'm going to do it in such a way that I, to the best of my ability, fill in most of the face portrait. I think that's enough. By the way, use Runge-Kutta method for this. It's better when you run this system. So I hope you recognize the saddle shape. Let's focus on the point 1, 0. But the thing I want to point out is that it kind of looks like a saddle, but with a major difference. So remember, for purely linear, for actually true linear systems, the saddle is created along those straight line solutions represented by the eigenvector. So in a true saddle for a linear system, these will be straight lines, the way I go over the mouse right now. These will be, for example, the eigenvalue corresponding to the positive the eigenvector corresponding to the positive eigenvalue, and this one corresponding to the negative one, because the arrows come toward the equilibrium point. So these will be straight lines in the linear case, because these will be eigenvectors. Now notice, if you look carefully, these are no longer straight lines, right? They are curved, because this is a non-linear system, not a linear one. However, if you zoom in close to the point, so the point was 1, 0, let's enter a viewing window which is very, very close to 1, 0. So for example, the interval for 1, let's take it 0.8 and 1.2. And around 0, let's take it minus 0.2 and then 0.2. Now, if I zoom in close enough, with the naked eye, you won't be able to tell that this is a nonlinear system. That's the whole point. Remember when I said for a single ODE, if you look at the tangent line close enough to the tangent point, you may not be able to distinguish the tangent line from the actual graph, because if you look close enough, the line is pretty close to the actual graph. Analogously, basically, if you look close enough to this point, you won't be able to tell that this is actually a nonlinear system. And you may think that it's a linear system with a saddle point. Although these things that appear like straight lines are not really straight lines, are curved. Now the system given by the Jacobian matrix is what you see here essentially, right? So the Jacobian matrix is the linear system that approximates locally the equilibrium point, provided again this Jacobian matrix doesn't have 0 eigenvalues or 0 real part. If the eigenvalues are complex. So in that sense, we say the point is a saddle. It resembles a saddle via that approximation. Okay, so that being said, let's actually go back to the viewing window from -5 to 5 to see the things from, see the whole thing from a larger perspective. Let's clear the curve and ask the system to do it again. And then the other point, obviously, it's a spiral. I'm not going to zoom in again, but this is pretty obvious, right? So remember, -1, 0 was a spiral, repelling spiral. So just to keep in mind, you have a linearization for each equilibrium point, because each Jacobian is evaluated at the equilibrium point. That's why you have a different behavior around the point 1, 0 and a different one around the point -1, 0. These are local property. There's an entire theory about global stability, but we don't get into that. So the Jacobian method, it's a method of analyzing the local stability around the point. Okay, so let's move on to another example. Let's see, what was the next one we did? We did the one with the circle, yeah, the one with 4 minus x minus y. That one had a saddle and a stable spiral, and x squared plus y squared minus 16. because the equilibrium points are 0, 4, 4, 0, let's make a viewing window a little bit larger. Let's say minus, let's clear the curve in the meantime. So let's say minus 7, 7, just to see the equilibrium points better. So one equilibrium point was 0, 0, 4 over here on the y-axis, and the other one 4, 0. So 4, 0, do you see it's actually a stable spiral, right? I mean, I kind of see already. Let's clear the curves again. So click on this. So the solution approaches the point via spiral motion. So again, a local property, if I click on a farther from the point, is not going to approach the point 4, 0. You got to start close enough to the point to see the stable spiral. And the other point was the saddle. It's a little bit harder to see it here. The saddle is over here, but it's very stretched because the solution either goes up or down very quickly. But anyway, this is where the saddle is, the other point, which was 0, 4. And let's finish the discussion with the example for which the Jacobian doesn't work, just to be aware how these computer plotters will show that situation. So x prime y minus x times x squared plus y squared. So remember, the Jacobian showed complex eigenvalues with the zero real part, which in the linear classification, remember, that would be a center, like fully periodic solutions. But that's not the correct conclusion, right? I mean, you simply don't derive any conclusion from the Jacobian once you have a zero real eigenvalues or complex with zero real part. So let's enter the system. And what will happen here is that I mean, see, it's hard to see what happens around the point. Although actually, if your guess is a stable spiral, that will be correct. But remember, we show that stability not by the Jacobian, but via changing the system in polar coordinates. However, let's say you're not certain and you decide to go close to the point. Let's zoom in close to the point 0, 0. So I say, let's say minus 0.2, 0.2, the new viewing window, or the new box for the point. And so see, if I click on the point, it's inconclusive what happens. I mean, you may think that this is a stable cycle, for example, right? Does the solution converge to a cycle? Or what happens? Well, let's pick another point close to the 0, 0. Now I have another set of curves very close to each other. So it's very misleading, you know, because if you're very close to the point, you may think it's a periodic motion, but in reality, it's approaching the point very slowly. And the reason it stops and it doesn't fill in that dot, it doesn't look that it's approaching the actual point, is because there are a finite number of iterations in any numerical algorithm. So the algorithm that generates this solution has a stopping point, essentially. I mean, the number of iteration needs to stop at some point. And I don't think if you change the method of integration, you're going to see much improvement. I mean, you still have the algorithm breaking down at some point. So that's why it's important to know the theory behind it, right? I mean, the Jacobian method doesn't work, or it's not applicable in these situations. So that's it for this lecture and for the course itself. Goodbye.